All right, thank you all for coming. So about me, I've been working in Python since about the year 2000. My first 12 years of Python work was in music, in fields of algorithmic music composition and computational musicology. Since about 2012, I've been working in finance, where I build production systems for financial modeling and product production at a firm called Research Affiliates, just south from here in Newport Beach, California. I'm also the author of Static Frame, which I will be talking about a bit in this presentation. So one of the points of departure for this presentation was the fact that the panel is deprecated, and I happen to have a lot of legacy code that uses the panel. The panel, if you don't know, is actually Panda's namesake, as far as I've heard. Panel data was combined to form pandas, and that's how pandas got its name. However, the panel is going away while it's still being a useful container of three-dimensional data. So now deprecated, what do we do? There's a couple of options. There's Xarray, there's pandas with hierarchical indices, and there's static frame with hierarchical indices, and we'll look at these and compare some of the options we have between these. So let's step back first and consider, why do we need more than a two-dimensional table? So for example, if we have a very simple data frame here, where we have 4 rows, each of those rows might be observations, here labeled A, B, C, and D, and we have 2 observations, X and Y. So we can select values from this data frame using the lock interface. I call this lock, you might say LOC, I say lock. We can use the lock interface to select one label per axis. And these selections are delimited by commas. So we can select rows and we can select columns, and they're nicely delimited by a comma in our lock call. So for example, if I want all rows from C to the end, I can provide a slice from C to the N with a 1-argument lock call. Using a second argument, here Y, I can select all rows from C to the end and column Y. All right, what about multiple tables? So we might have multiple sensors performing similar observations, and we might want to store these in a single data structure. A natural choice is a Python dictionary. So for example, here I can create a second data frame of the exact same shape, and I can store this in a dictionary. And I can, here I'm giving the dictionary keys Roman numeral 1 and Roman numeral 2. And I can pull off a row from Roman numeral 2 using the lock call of C. And I can average across these 2 data frames. But this gets pretty awkward here, as you can see. We lose the opportunity for contiguous arrays, and we cannot easily select across frames using this approach. So the pandas panel offers a nice, or rather offered a nice way to deal with this. It's basically a 3D frame. It's similar to a dictionary of 2D frames with consistent indexing as we would find with a data frame or a series. And it was available through pandas 0.23. So we can actually create a panel from a dictionary of frames, and here that's what I'm doing. I'm giving my previous dictionary of 2 frames to the panel constructor, and now I have a panel. And we can see that the panel has labeled the outer axis, Roman numerals 1 and 2 as the items, the next axis, the major axis, as labels A through D, and the minor axis as labels X through Y. So we can select values from a panel extending the lock interface to 3 arguments. Where we would select first the items, then the major index, and then the minor index. So for example, if we want to select all of the outer items index and the major index C, we can do that with 2 arguments. With 3 arguments, we can select all of the outer items. We can select major item C and minor axis X. And then we can take the mean across the common element C across both of those tables. This is the operation we did previously with the dictionary. Now you can see it's much more readable and clear what's going on, and probably faster. Now, as I mentioned, the panel was deprecated in 0.23 of pandas, and there was this very nice warning given to us that encourages us to consider using the multi-index or Xarray. So let's take that advice and see what we can do with these 2 options. So we'll look at Xarray. If you haven't used Xarray yet, it's a library built on NumPy and pandas with rich support for multi-dimensional data arrays and data sets. So there's the 2 foundational objects in the Xarray library. Alternatively, we can get hierarchical indices, and there we're going to look at 2 implementations of hierarchical indices. We have the multi-index in pandas and the static frame index hierarchy. So we're going to step back a little bit and try to understand what a hierarchical index is. And before we do that, we're going to need to understand what an index is. And before we do that, we're actually going to need to go all the way back to NumPy, because Pandas is built on the precedent of NumPy. A key feature of Pandas is that it adds labels to the axis of NumPy arrays. But the Pandas lock interface is based on NumPy's getItem. And let me show you what I mean. So NumPy provides integer-based selection using the getItem interface. The selections available, some of them are like the Python list or tuple. So we can select single items or we can select slices. But NumPy goes further than the standard Python list or tuple. NumPy introduced the idea, as far as I know, of selecting arbitrary items through lists of integers or Boolean arrays. So we can see the examples of the 4 types of selection available in NumPy. Here I create an array of 8 elements, and first I'd simply select a single one with an integer. You're all familiar with that. I select a slice of the last 2 elements. Then I can give it a list of index positions and select those index positions, or I can do something more sophisticated and create a Boolean array by identifying all of the values that their modulo 2 are equal to 0, that is the even numbers, and use a Boolean array to select from the array. So NumPy supports n-dimensional arrays, which means we can produce extremely complex structures, and we can perform the same types of selection on each axis independently. Each selection can use any of the 4 selection methods. And as we've seen in other cases, each of those selection methods is separated by a comma. So, for example, if I have a 2-dimensional NumPy array, as I show here, I can select rows 1 and 3 with my first argument to the getItem, and I can select columns from -2 to the end using a slice for the second argument to the getItem call. If I have a 3-dimensional array, I can simply continue the same pattern. So if I want to select specific elements, I can provide 3 arguments, 3 integers, and get to 1 item. If I want to select the first 2 dimensions with an integer index and a slice for the third, I get an array out of that. And if I want to do something even more complex, I can select a single item from the first axis, a list of items from the second axis, and a slice from the third axis. So now we're ready to talk about what an index is. The index is an object that maps labels to positions along an axis. The lock interface exposes access to index objects on rows and on columns, and the labels can be given with the same 4 selection types that NumPy provides us with. As with NumPy, the comma separates selections per axis. So as we've seen before, with the data frame, we can use the lock call to select 2 rows, here A and D, and 1 column X. All right, so now we're ready to talk about a hierarchical index. A hierarchical index is a multi-level mapping applied to a single axis. 2 levels can describe 2-dimensional data, 3 levels can describe 3-dimensional data, and we can go to unlimited depth, really. Each level supports the 4 selection types that we've already introduced. And there is more than one way to implement a hierarchical index. So with the Pandas multi-index, we can create a multi-index using the from product constructor. It's going to take 2 iterables, one here of Roman numerals 1 and 2, the second argument of letters A, B, C, D. That's going to take the product of those 2 iterables. We can feed those to a data frame, and we can get a nice data frame that has a hierarchical index on the rows and columns labeled A and B. And so from everything we've seen before, we know that if we provide 2 arguments to the lock call, the first argument is going to select the rows, and the second argument is going to select the columns. So in this example, we're providing the null slice as the first argument to select all rows, and we're supplying B to select column B. But what do we do when we want to get inside of the hierarchical index? With NumPy and index objects, we've seen that commas separate the axes. But how do we select the inner depths within a single axis? We cannot just add more commas. It's ambiguous. So for example, if I have a lock call with A, B, and C, A and B could refer to the rows and C could refer to the columns, or A could refer to the rows and B and C could refer to the columns, or we could actually be trying to do some sort of a 3-dimensional selection, as we've seen with NumPy or the panel. So we need to delimit the hierarchical selections within an axis selection. So we need some way to group these inner selections. And here I'm showing an example using caret characters, but in pandas and static frame, we actually use a special object. In pandas, this special object is called the index slice. In static frame, we call it hlock. So with the pandas multi-index lock, we can do our index slice on one axis. And as you might expect, here I provide an index slice that's getting into the inner specification of the hierarchical index. It's saying, give me all of the outer level Roman numerals 1 and 2 and rows B from each of those, and then select one column, here now selecting the rows with B. We can do the same with a two-dimensional data frame. So, I mean, with a index hierarchy on both the columns and the rows. So here I provide two index slices, and again, there's two arguments. The first argument to lock is an index slice that's grabbing the second Roman numeral and rows A and D, and the second argument to lock is another index slice that's grabbing all of the outer level and just columns B. So this is very clear and very consistent, almost. Now, in general, I have a strong conviction that complexity should be balanced with consistency. And as you can see, these multiple axis, multiple selection types, things can get very complicated. We want our hierarchical indices to be consistent with non-hierarchical indices and NumPy selection methods. This consistency is important to me. My background is that of a software engineer more than a data scientist, so my concern overwhelmingly is in readability and maintainability of our code. And what I find is that the pandas implementation is not consistent. So, time for a quiz. What should these lock selections do? If we look at this example, we have a lock that has two arguments. One is Roman numeral 2, the other is B. In the second example, we have a slice and we have a B. You don't have to shout it out, just try to think about what this should do. Well, in the first case, we have two arguments, but those two arguments, Roman numeral 2 and B, have selected just from the rows. Now that violates everything that we've seen previously in NumPy, in single-axis selection, where the first argument refers to the rows, the second argument refers to the columns. Now if we change the first argument, if the first argument just happens to be a slice, now it works as we expect. We get a row selection with the first argument and a column selection with the second argument. That's inconsistent. Okay, here's your next quiz. I have the first case where an index slice is being used. We've seen how index slice allows us to group inner selections within an index, within a hierarchical index. So we see the first example where we have an index slice that's specifying what we would think the outer level to be everything and then the inner level to be B and D. And then we have in the second example a two-argument call to lock where we provide a second argument here, B. So think about what you might expect this to be. All right, so in the first case, we provided one argument to lock, and that was wrapped in an index slice, which we thought would specify selection inside of the hierarchical index. But what happens instead is that the one argument index slice is treated as two, one specifying rows and the other specifying columns. If we provide a second argument to the lock, then this changes. And suddenly we get something closer to what we expect and the well-established precedent of NumPy, which is that the first argument refers to the rows and the second argument refers to the columns. So, as Raymond Hettinger often says, there has to be a better way. Part of these inconsistencies led me to build static frame and for a desire for a more consistent and explicit interface to these types of tabular structures. In static frame, all data is immutable, all indices are unique, and we have comparable features and performance to pandas. It is dependent exclusively on NumPy, and it's written presently in pure Python. Now, as a second phase, we're planning to look for further performance enhancements, but as of this time, we are just pure Python. So static frame introduces the index hierarchy, which is a new implementation of a hierarchical index. It's built with non-hierarchical indices, which ensures that it has consistent selection features between index and index hierarchy. It also fits in with this desire for consistent delimiting of access specifications. And the way that's done is with hlock. So hlock is similar to the pandas index slice, except it's always required for inner depth selection, and it's always applied to only one axis at a time. sflock is a sibling to another object called ilock. hlock permits hierarchical selection within a lock. ilock permits index position selection within a lock. I won't talk about ilock further, but the two are sort of siblings, if you will. So using static frame, we can create an index hierarchy using a similar constructor to what we saw with pandas, a from product, which is going to take two iterables, produce their product and give us an index. And we can again create a static frame that uses that on the rows index. With static frame, we have consistent axis selection. So in the first example here, where pandas did something kind of surprising and treated the two arguments as both applying to the rows, here static frame says this is ambiguous. I don't know what you're trying to do here by giving me this notation, and instructs us to actually use an HLOC. We need to specify that we want to get inside of the hierarchical index for our rows. Another example here, we see that we can use an HLOC to specify one argument to a lock, and it's completely unambiguous that we're selecting within the hierarchical axis on the rows. So here we're taking an HLOC of all of the outer level, and we're taking the inner level of B and D, and again, this is one argument, so of course this should apply only to the rows. All right, so we're going to now look at some real data which is suitable for hierarchical indexing. What we're going to do is look at some time series from multiple instruments with multiple characteristics. And we're going to use 3 dimensions, a sensor identifier, a timestamp, and a bunch of observations. So as a point of departure, we're going to use this article from the Orange County Register from last year. This was on December 17th, almost a year ago from today, where the news reported that big surf was possible, a massive swell was going to come, prompting National Weather Service to issue a high surf advisory. All right, so we're going to see if there was a massive swell on December 17th and use this as a case to get some data to play with. So if you haven't known yet, you can go to the National Data Buoy Center and get data on all these buoys. It's actually quite interesting. I found 3 buoys off the coast of Southern California that seem to be plausible candidates, San Pedro South, and Santa Monica Bay. And we can pull a year's worth of their data. Now, it comes from the NDBC in this slightly awkward space-delimited format, so we're going to have to parse this and construct the timestamps into meaningful timestamps. We're going to convert the wave direction degrees into compass labels, and we're going to convert the wave height and wave period into floats. What our expectation is that large wave heights and large periods, that's DPD, should correspond to this massive swell we're looking for. So we're going to store this in a 3-dimensional data structure, and we want confirmation from multiple buoys. That's why we want to take multiple observations. So we're going to have 3 buoys, 1 year of date time samples, and 3 attributes per sample. And we're going to look at a couple 3-dimensional data formats that we can use. We have the pandas panel, we have the X-array data array, and we have hierarchical indices and pandas and static frame. We're going to look at 2D hierarchical index on a frame, and a 3D hierarchical index on a series. So let's start with the panel. So if we load this data into a panel, we can see the string representation we get out of the panel there. The buoy identifiers are coming in as the items axis. The major axis are the timestamps, and the minor axis are the observations, here DPD and wave height WVHT. Now, the string representation of the panel makes exploration a little bit difficult, and that's something that we're going to bring up later on. This is sort of one of the challenges of visualizing data, 3-dimensional or higher dimensional data, on a 2-dimensional screen. So in X-array, we can create the exact same structure, and we're going to actually use the panel's 2X-array method to do this. So it's going to give us an X-array data array object with coordinates labeled items, major axis, and minor axis. They're labeled that way because they came from a panel. They could be labeled anything we want. Now, the string representation shows a bit more information than the panel, but I would argue it's still a little bit difficult to explore. Now we're ready to look at hierarchical indices for the same data, and we can actually represent the same 3-dimensional data in 2 different ways using hierarchical indices. We can create a 2-dimensional hierarchical index on a frame that has 3 columns, where the index is a hierarchical index of station ID and date time, and the columns are our period, our wave height, and our wave direction. We can also go further and collapse all this information onto a single array and use a 3-dimensional hierarchical index on a series, where our index becomes station ID, date time, and the attribute is here wave period and wave height. This is where the title of my talk comes from, because it is the case that any n-dimensional array can be reduced into a single one-dimensional array with sufficient hierarchies. But we probably don't want to do this. It will lead to undesirable type coercion if we have everything in one array, and will often lead to painfully slow selection because you're breaking up things that you should have kept separate to begin with. So this is generally not advisable. So here's what the data looks like in a two-dimensional pandas frame, where we have as our index the station ID and date time timestamps, and we have wave height, the period, and the wave direction. In a static frame two-dimensional frame, a static frame with a two-dimensional index, we see something very similar. Now with a three-dimensional index on a series, again, we're packing all of the information into one place. So we have the station ID on the outer level, the timestamp in the middle, and the attribute, either the period or the wave height, in the innermost level of the index, and we've reduced everything to a single one-dimensional array. And we can do the same thing with static frame, as you see here. So it's useful to consider at this point that representations matter. Hierarchical indices provide practical string representations, and that's important. When viewing numerical or character data on a screen, a two-dimensional layout is actually best. So one feature of hierarchical indices is that they pack many dimensions into a readable one-dimensional representation. So now we're going to look at some performance comparisons between these different three-dimensional representations and try to get an idea of how some of the performance varies amongst these and what the trade-offs are when using these different representations. So we're going to look at three scenarios. This is far from exhaustive, but we're going to look at three. We're going to look at a single buoy, a single date time, and a single attribute. How long does it take us to drill down to that single element? A single buoy, a date time slice, and the mean of a single attribute. And then we're going to look across all buoys, a date time slice, and then get the max from some selected attributes. I'm going to be using pandas 0.23.4. I know this is a couple versions back, but it was the last with a fully functioning panel, so that's why I chose it, and a recent version of static frame. We're going to do 500 iterations of these for each of this test we're going to give, and the code to reproduce all of this is available within the static frame library. You can find it there. So again, interface is important. Let's look at the interface. We can see our single buoy, single date time, single attribute selection on a panel and on the X-array data array is exactly the same. These two lock calls are exactly the same, and consistent with what we've generally seen, we're selecting one axis at a time. First, the station ID, then the timestamp, and then the attribute we're looking for here, that's wave height. For a two-dimensional frame, either in pandas or static frame, we can use an index slice with pandas to select the outer and the inner component of the rows index, and then wave height from the columns. From static frame, we're going to use an hlock to do the same. For the three-dimensional indices on series, we provide all three arguments in one go. For pandas, we don't have to wrap this in anything. It's going to just assume that that's correct somehow. For static frame, because we're more strict, we're going to require that to be wrapped in an hlock because we are specifically reaching into a hierarchical index. So here are the results from this first test. We see that direct selection of a 3D index is fast. We're just drilling down into single values. And both the static frame and pandas three-dimensional index on a series here is actually pretty fast. The panel is faster than the pandas data frame with a 2D index. That's a trend we're going to see. And we could consider that the static frame index hierarchy may have some advantages here, but I'm not too wedded to that claim. Moving on, so if we look at a single buoy, a date time slice, and a single attribute mean. So here we're using a feature of date time indices where we can give it a date and it will select all of the observations across that day. So we're actually picking up a slice of date time observations across an entire day. And this is one of our targeted days, December 17th, by the way. So we can take a mean from both a panel or from an X-array with the same exact interface. For a two-dimensional index on a frame, again, we use index slice or hlock, depending if we're using pandas or static frame. And again, in this case, the interfaces are identical. For working with the three-dimensional index on a series, in this case, I couldn't get pandas to match the entire date for one reason or another. So I actually had to construct a slice between the timestamps. For static frame, we can just give it the date and everything works consistently as we would expect. So in this case, the static frame two-dimensional index performed pretty well. the panel was again faster than the pandas data frame with a 2-dimensional or a 3-dimensional index. And we start to see 3-dimensional indices start to really suffer, and pandas' 3-dimensional interface suffering quite a bit. So as you might expect, with the depth of our index growing, we have to do more and more selections to get at those inner values, and that begins to get costly. All right, our last performance test is looking at all the buoys, a date times slice, and we want to get the max value from that slice. So in the panel and in the X-array data array, the interface is kind of the same, but the axes kind of flip in a funny way. So I have to provide different axis arguments here to get the same result. For the 2-dimensional index on a frame, pandas and static frame are basically identical in how they present the way to get this value. And when we move to on a 3-dimensional index on the series, things get a little bit tricky because we want to get the max from 2 attributes. So we actually need to iterate over those attributes, select a value, take the max, and we actually have to do that twice. So as you might expect, those are going to get pretty slow. So in this case, the panel wins. The panel is the fastest, and yet again outperforms the data frame. The static frame 2-dimensional index on the frame does pretty well. X-array is similar to the kind of in the middle as it's been. And we start to see, as we get to the 3-dimensional indexes, a serious degradation in performance. Static frames, multi-index, really suffering at this high depth. So what we see here is that the panel consistently outperforms comparable data frames. The X-array data array has performance and interface similar to panel, and that's pretty good. Static frame is sometimes faster than pandas. Some 2D index operations appear to have advantages. The 3D index operations are far slower. I don't put too much credence in these performance tests. They are rather shallow, but it does give us some interesting indications. Again, static frame is pure Python now. As you probably know, pandas has lots of C and Python under it, so we will be looking to do performance enhancements to static frame in the future. So again, these performance tests are shallow. We could explore larger data scales, we could perform alternative selection combinations, and we could look at different memory usage to get at what we're doing under the hood here. So to return to where we started, the panel is deprecated. What next? For the most similar performance and interface, using X-array is a great choice. If you are refactoring your code, as I am doing right now to get the panel out of our code, consider moving to static frame. If the pandas data frame with a multi-index, in fact, may be slower than X-array, your previous panel code, and possibly static frame in some cases. So let's return to this guy. Big surf, possible flooding and erosion, massive swell. Can we find that massive swell in this data? Well, we can, and I actually took a very simple approach. Here we have, again, in a static frame, the 3-dimensional data with a 2-dimensional hierarchical index on the rows. What I'm going to do here is first take the mean across all buoys using a 2-argument call to look, and I'm going to add 2 times the standard deviation to get a threshold for wave height. I'm going to do the same to get a threshold for wave period, but here I'm just going to use 1 standard deviation, and I found this through experimentation. So I found 2 thresholds around the mean, plus or minus 1 or 2 standard deviations, and I'm going to use a Boolean selection on a lock call. I'm doing the Boolean intersection of 2 Boolean arrays where I find the values that are greater than the thresholds I found, and that gives me a bunch of target records, and we can see those target records there. So now all I need to do is reduce the timestamps into dates. So I'm going to do that by iterating over the values in the index and calling date on them to get a date object. And then I can simply do a group by on the dates and apply a length function. One of the features of static frame is that iteration and function application are unified in every case. There aren't 2 functions for those with various confusing names. So we can iter group on date, and then we can apply a length function. And this gives us a series that shows us that, in fact, on December 17th and December 18th, the number of high wave periods and high wave heights was actually truly massive, and actually, some of the highest days by far across the entire year. So use X-array if you want something similar to the panel. Hierarchical indices do add overhead, and of course, the more depth, the more overhead, but what we've seen is that 2-level depths are pretty efficient. It's also useful to consider that the string representation of the hierarchical index actually matters and helps in data exploration. Finally, consider using static frame if you care about immutable data, you want more consistent interfaces, and in some cases, maybe better performance. Thank you. Any questions?
What do you think is causing the 3D static frame to be slower than the other two?
Well, we see that the three-dimensional index is always slower when we start getting at the inner level. The static frame index is built with just Python dictionaries. So we're bound by the dictionary lookups, and we're at the inner level, we have to do a bunch of those. As you may know, Pandas has its own dictionary implementation that they've refined and specialized over the years. So, but actually, I don't even think they're actually using that in their hierarchical index. They're doing something kind of different. So that's something for us to look to for performance improvements.
So I'm curious to know if you've ever tried running something similar, a query similar to this, with just loading the data into an in-memory SQLite database and running a SQL query against it, just to get a sense of what the kind of performance you get there versus all of these different approaches.
Yeah, that would be great to look at. Of course, with SQLite, we don't really have a hierarchical index, so we would have to lay out the data in some other way or do something a little bit different. I did benchmark this against pure NumPy using just direct selections through dictionaries, and NumPy wins hands down in every case. I didn't show it here to keep things simple, but NumPy direct is by far fastest.
Gotcha.
SQLite, we use SQLite sometimes for similar cases, but fitting hierarchical indices in SQLite becomes awkward, obviously.
Okay, good times, thanks.
Yeah. Anything else? Great, thank you.
Thank you.